Hello everyone. This is my question for end-term examination. Modeling and computational fluid dynamics analysis of steady mixed convection in a lead-driven cavity using suitable software package. You can choose the relevant dimensions of the cavity, fluid properties, lead velocity, boundary wall temperatures as per your convenience. So here I have considered a 2D model consisting of 10 centimeter and 10 centimeter square cavity filled with air, whose lead velocity is 0.01 meter per second at the top wall. Properties of air, here density dependence on the temperature is defined using Bosniak's approximation, where rho is given by rho naught into 1 minus beta t minus t naught. Uh, for our problem, we have considered these values, and boundary conditions are here. Hot wall is at temperature 310 Kelvin with no slip condition, and cold wall is at temperature 280 Kelvin with no slip condition, and bottom wall is insulated and no slip condition, and top wall is with a velocity 0.01 meter per second as mentioned above. Now we have to perform steady state analysis in Ansys fluent and plot these six uh, isotherm streamline, temperature contour, velocity contour, horizontal and vertical central velocities, temperature variation at top wall. So here the note, convergence criteria for normalized residuals of the continuity and momentum equations are set at absolute values of 0.001, which is by default in the Ansys, and for energy equation is set at 10 to the power minus 6, which is also by default in the Ansys, and mesh size is taken as 100 into 100. Uh, so let's go to the Ansys workbench. So we'll first break down the Ansys fluent, then we'll go to design modular to design our uh, square cavity. So let's wait for it. So now for uh, drawing the drawing our sketch, we'll first click on the z-axis to get the xy plane view. Then we'll go to sketching, click on rectangle. Of first, let's change the unit to centimeter because our square cavity is 10 centimeter to 10 centimeter. So now we'll draw the rectangle square like this. Now let's give the dimension, this dimension and this dimension. Our cavity is 10 centimeter, 10 centimeter, so this is 10 into 10. So next we'll go to concept. From here we'll select surfaces from sketch, click on the xy plane, select sketch 1, apply, and then generate. Now we'll have surface body here, whose this part is as set as solid, so we'll change to fluid because our material in the square cavity is filled with air, which is a fluid. Now next we'll generate it, and then we'll update the geometry here, so it is updated. Now we'll go to mesh. Before that, let's close this design modular. Okay, now let's wait for the mesh. So here the let's click on the z-axis to get a xy plane view. Now first update the mesh. So this is the by default mesh generated by the Ansys workbench. Now let's refine this mesh. First we will insert face meshing and select this face, apply, and then we insert sizing. We'll size the edge of the square cavity. So select the edge, select this edge and this edge by using control button and apply. Change this type to element number of division. Since we have the mesh size is 100 into 100, so we'll uh, give the number of division here 100. Also we'll give biasing because we need more at the corners, more accurate properties at the corners, so we'll give this bias and bias vector as 2. Now same with the, now we'll insert same sizing in the left and right wall. Let's select this, yeah. And next we'll change the type to number division. Number division will be 100 here as well. Next biasing, same as the previous one, the third biasing type, and bias factor will be 2. So these are mesh. Now we will update the mesh to get our desired result. So this is the mesh we have generated. Now let's create the name selection. So this is as per our problem. We can see that this is the top wall, this is the cold wall, this is hot wall, and this is bottom wall. So let's name this. So this is what? Let's select this. This is a top wall. So top wall. Okay. Next, what is this? This is bottom wall. Bottom wall. Okay. Next. Uh, next. What is this? This was cold wall, right? Yeah. So this will be cold wall. Next, this will be hot wall. Okay. Okay. Next, you can see here the this is top wall, right, and bottom wall. Yes. Cold wall. Yes, and hot wall. Okay. Fine. So the mesh is generated, and we have named the selections, named the walls. So let's update the mesh now. Okay. Here we can update the mesh. It's updating. Yes. Fine. So we can now close the mesh window. Okay, now we'll go for setup, edit. Uh, Now is we'll select double precision and process type server process one is fine for this problem. Okay, we'll now start. Okay, it is taking time. Okay, so these are model. Now first we'll give the gravity. So this is downward direction. So we'll give in the y direction as the value minus 9.81 because since the direction is downward, so it will be minus 9.81 meter per second square. Okay, fine. Next model. Model, since the is a mixed condition problem, and also here temperatures are there. There is hot wall and cold wall are there, so we'll on the energy, and it is a steady problem. So viscous will be obviously laminar. So yeah, laminar. Then we'll go to the material fluid and double click on the air. So what is given the problem is given is a Bosniak approximation. So here an option is there, the density, yeah, this. So we'll click on this, and then we have to give the value of rho naught. This is given the problem, rho naught, this. So let's click on this, copy, yeah, copy and paste. And others are, yeah, others are same, cp mu k conductivity, others are same. So just we have to give the thermal expansion coefficient beta, and beta is given in the problem as well, this value. So just copy it, yeah, copy it and paste it, fine, and change and create. Okay, change and create, close. So properties are given to the here. Now next is boundary condition. So click on the boundary condition. Bottom wall is, yeah, so we can see here boundary condition. Bottom wall is insulated no slip, but in Ansys it is by default insulated and non slip. So we do not need to change this bottom wall's boundary condition. So we'll go to directly go to cold wall boundary condition. Okay, so it is, so we are given a temperature of 280 and no slip. So we'll go to thermal and click on the temperature and give this as 280 Kelvin. Fine, apply, yeah. Then we will go to hot wall. Water temperature is given as 310. So same, go to temperature and click on this and C110, C10. C10 is okay, fine. Next you have to give top wall. So here in the top wall it is insulated and velocity is given as 0.01 meter per second. So it is not stationary, it is moving wall, and velocity will be 0.01 meter per second. Okay, fine. Apply. Yeah, it's applied. Close. Next we'll have to go to the run calculation, and number of iteration, let's give it as 1000. And now initialize. So we'll initialize as hybrid. Oh, before that we have to select the method. Yeah, method. So method will be here. Scheme will select a simple. Pressure we can select as presto, and others we are keeping it as default. Next, again we have to initialize. So initialize, go to run calculation and calculate. So it is calculating. Yeah. So calculation is completed, because this you can see this here, you can see here. Yeah, this, yes, this 134 iteration the solution is converged, and these are the values. Okay, so since the solution is converged, so the calculation is completed. Now we will go for post processing, which will include these taxes: isotherm, streamline, temperature control, velocity control, horizontal, vertical, center, velocity, temperature based on the top one. Okay, first we'll go for isotherm. So for isotherm, let's go to graphics, contour, double click on it, and make it isotherm. Isotherm. Okay, isotherm. Then pressure is changed to temperature. Field is unclicked, and 7 display. So this is the isotherm we got. Here you can see that we given this as hot wall, right? So here the temperature is maximum. It is 310 Kelvin. This red zone, and here it is blue zone is minimum temperature cold wall, that is 280 Kelvin. You can see the isotherm lines as well. These are the lines. These red lines are the high temperature line, and blue lines are the low temperature lines. Okay, fine. So next, as this is completed, now we'll just update the result first, and then we can close this one. Yeah, we can close this one. Next, after closing this, we'll go for the further post processing processes. So for that we will go to the results edit. Okay, so let's wait for few seconds. So next our tasks are streamline, temperature control, velocity control. Okay, so let's first click on the Z axis to get a XY plane view. Click on the insert. So click on the streamline, and we need velocity streamline, right? So let's make it velocity streamline, velocity streamline. Okay, fine. Okay, start from symmetry 1, and number of points we can give it as 100. Symmetry 1 streamline equal stress, velocity, apply. Just apply it. Okay, so it will take a few seconds for, so let's wait. Okay, so here is the velocity streamline. The red zones are the maximum velocity points, and the blue zones are the minimum. So here you can see these are the maximum velocity points, and these are maximum velocity. So okay, next we have to go for temperature and velocity control. So first unclick this. Yeah, so next control will go for temperature control. Okay, temperature control. Click symmetry 1, variable give us temperature. Let's number control is 100. Apply. Okay, so this is the temperature control. It is similar to the isotherm lines. You can see the this is the hot wall, so the red zones are here. This is highest temperature 310 Kelvin, and this is the lowest cold wall. So these are the lowest temperature points, 280 Kelvin. You can see the values here, highest and lowest values, and these are the middle or the mixer of what hot and cold walls. So yeah, next, so let's unclick it and insert contour. Next, velocity contour. Velocity contour for that sensitive velocity. Bottom one is sensitive symmetry 100 and apply. So this is the velocity contour. This is also similar to streamline, velocity streamline. So yeah, next we'll proceed for the next task, that is 56 horizontal and vertical central velocities and temperature present in the top one. So for that, we will first need the vertical and horizontal center lines and the top wall line. So for that, we will first locate those lines. So location line. First, let's locate vertical center line. Vertical center line. Okay. So the point will be vertical center line. For the point will be the point one will be 0.05 and 0. Here z-axis point will be 0 because it is a 2D problem we are doing. So here also it will be 0.05 and this will be 0.1, and we can give it as 100. Okay, for our convenience. So let's apply. So yeah, this is the yellow line is the vertical center line. Okay, now next similarly we'll do it for horizontal and top wall line. Horizontal center line, top wall line. Okay, insert location line, horizontal center line. Fine. Okay, 2 point. So for horizontal center line as well, it will be 0, 0.05. So the axis will be 0 because it's a 2D problem we are doing. 0.1, 0.05, 0, and it will be 100. So let's apply it. Yeah, this is the horizontal center line. Next, similarly, we'll go for the top wall line. Top wall line. So for top wall line, uh, we'll have the point 0, 0.1. So here also the z-axis point will be, z coordinate will be 0 because it is a 2D problem. 0.1, 0.1, 0, and 100. Okay, fine. So let's apply it. Yeah, so this yellow line is the top wall line. Okay, now we'll go for the variation search. So first we'll go for the horizontal center line velocity. Okay, so okay, first give it the name as horizontal center line velocity. Let's copy it and also give the title as, oh yes, no, it's not copied. Okay, next we'll give the x-axis as start count and y-axis as u velocity. Okay, so let's also, yeah, location will be horizontal center line, right? So apply it. Yeah, so this is the horizontal center line velocity. Velocity is not, yeah, I applied. Yeah, so this is the horizontal center line velocity. Now similarly we'll go for vertical center line velocity. Vertical central velocity. So let's copy it, and location will be vertical center line, axis will be short count, and y-axis will be here. Since it's a vertical center line velocity, so it will be the component along the y-axis, that is velocity v. So let's apply it. So yeah, this is the chart we got, horizontal center velocity variation. Okay, next, similarly we will go for the temperature variation in the top wall. So click on the chart, and here write it as temperature variation the top wall. Okay, next click on the OK, and give it as the same name as you given earlier, temperature variation at top wall. Okay, so let's copy it and give it here as well. So it's not copied, I guess. Let's copy it. Okay, visualization the top wall. Touch this location, we select is a top wall line, and x will be short count, x-axis will be, and y-axis will be temperature. So temperature, fine, apply. So yeah, we can see here the line is like for the this is the hot wall. So here the temperature is maximum 310 Kelvin, this point. And as we progresses in the right direction, the temperature is decreasing gradually, and then at near the cold wall, it is with decreasing very fast with uh, with reaching this point 280 Kelvin at the cold wall. So this is the variation, right? So we have completed our all the tasks. Let's see all the what we have done. So this is the temperature variation at the top wall. This is vertical central line velocity. This is horizontal central line velocity. And next we'll click on 3D viewer to this is the temperature contour. This is the velocity contour. This is the velocity streamline. This okay. So we have completed all our tasks. Let's update it. Okay, so we are updating. And next we'll just save our file. Since I have already named this entire assignment, so it will not take much time. Just progressing it here. So yeah, so we have saved our file. So this is the all we have done in this assignment. Thank you.